A tidal stream environment is a coastal area of water that experiences current velocities in excess of 1 meter per second. This fast-flowing water interacts with the seabed and other geographical features to produce turbulence and creates unique hydrodynamic features that are often visible at the surface. These can take the form of bed-derived flow structures such as colks, bursts and colk boils, coastally derived features like eddies and wakes, or open water assemblies such as tidal jets. It is these colk boils that we will try and examine in this video. These are turbulent features that arise when fast-flowing water hits a ridge or crest on the seabed and water is spun into a vortex as a result. This is known as a colk, and this colk travels upward through the water column and erupts at the surface, creating a circular or elliptical patch of smooth water when it breaks it. This is surrounded by a visible perimeter of bubbles and waves, and these rotating masses of water are thought to trap both sediment and smaller animals with it. As colk boil formation is linked to the flow of water interacting with the seabed, this may mean that over the tidal cycle these features could become predictable, localised hotspots. For top predators, this may mean prey is forced closer to the surface and becomes more accessible, or for others may be increasingly aggregated in certain spaces during specific time periods. These areas are also attractive to tidal energy developments due to the reliable fast-flowing current speeds exhibited within them. So if these areas are already providing localised foraging hotspots, what impact will placing a tidal energy device in the same area have on the hydrodynamic features such as colk boils and the prey and predators which are interacting with them? How can we find out? Drone imagery offers a cost-effective method to collect fine-scale data sets of surface hydrodynamic features within a tidal stream environment. So what are we trying to measure from drone imagery? Well, this includes trying to differentiate between whether there are different types of colk boils. For example, are they formed or unformed when we observe them within a picture? This could be an indicator as to how much energy is associated with it. Formed colk boils are likely to have just emerged at the surface, while an unformed boil is likely to be dissipating back into the general water flow. We also want to know how large these features are at the surface. In doing so, we can learn more about how much turbulence was in that area and across different time periods as well. A larger colk boil is likely to be linked to more energy, as more energy has had to gone into creating it. And finally, we want to know the location of these features at the surface. This could perhaps indicate areas that animals may associate more highly with, but also areas of increased turbulence that may be useful to indicate to potential tidal energy developers. After processing 2018 drone imagery of colk boils in the Pentland Firth, Scotland, we found that distribution appeared to be significant across both ebb and flood tidal phases, with a distinct pattern being seen. In this area, the current direction moves from the right of the image to the left on the ebb phase, and vice versa for the flood. This indicates that potentially colk boils are being moved from their point of origin on the seabed some way before becoming visible at the surface. We also saw that predominantly boils appeared to range between 100 to 1,000 meters squared in size, but aggregations of boils much larger than this were also present, potentially indicating bathymetric features may be causing larger boils to appear at certain times on the surface. We also observed distribution based on current velocity, seeing that mainly boils were present in excess of 2 meters per second, with none being seen above 2.6 meters per second. However, surveys were undertaken at speeds higher than this, so it potentially indicates that a maximum velocity cutoff point for their appearance at the surface exists. So, in summary, drones provide a cost-effective tool for the characterization of fine-scale surface hydrodynamic features, and we're seeing that colk boils are being moved from their potential point of origin on the seabed and are aggregating based on the tidal phase and the prevailing current direction. Boil size seems to be consistent, but larger boils may be associated with specific features on the seabed at specific points. And finally, there appears to be a potential maximum current velocity cutoff point at which they are no longer becoming visible at the surface. Thank you for watching.